So chapter 11 is about virtual work, and this chapter is divided into three sections. In the first section we will go through the definition of work, and in the section 2 we will talk about principles of virtual work, and the last section we will discuss connected rigid bodies, and we will do one example to really understand the whole concept of virtual work in this section 3. So this principle of virtual work was proposed by Swiss mathematician John Bernoulli in the 18th century. It provides an alternative method of solving problems involving equilibrium of particle, equilibrium of a rigid body, or equilibrium of a system of connected rigid bodies. So basically it's just an alternative method related to what we were discussing before. So in previous methods we used equilibrium of equations to figure out if the system of rigid bodies or a system of particle is in equilibrium or not. So work is also one of the alternative method to see if the system is in equilibrium or not. So let us just first define what is work of a force. So basically we are going to define what is work in this case. So a force does work when it undergoes a displacement in the direction of line of action. So what this definition is saying is that a force will do work when the displacement is in the direction of its line of action. So what do I mean by that is if there is an object and the object, a force is applied on the object to move that object. So in that case, if an force, this was an original object, and when we applied a force, the object moves to some distance delta. So this is the line of action of force, and the displacement is also happening in the line of direction of force. So if that's the case, then we can say that this force has done work. So this is what this definition is saying. So I will give you an alternative scenario. For example, let's just assume you have one bucket and a person is holding a bucket and it's moving in this direction. So basically what's happening, and this bucket has a weight W. So what's happening is that a person is holding a bucket and it's moving in one direction. So this is the weight of a bucket. So weight of a bucket is acting downward. So if someone will ask you a question that does this weight is doing work or not, so the answer would be no, because this is the line of action of this force, which is weight, and there is no displacement happening in this line of direction. So that's why this weight will not do any work. So that's how we define work. If a force is producing a displacement in the direction of its line of action, then in this case you can say that this force is doing a work. And it also goes for the moment as well. If there is a moment and moment is producing an angular between the line of action of force, then you can say that this moment is also doing a work. So let's just say we have this force F, and this force is producing a differential displacement dr, and the angle between this displacement is this theta. So in order to find that this force has done work or not, we need to find the component of that force which is in the direction of its line of action. So that component of force, if we want to calculate the component of force, we already know theta. So if we want to calculate the component of force in the line of direction, then this component would be f of cos of theta. So this f of cos of theta is that force which is producing work, because this is that component of force which is in the direction of its line of action. So in this case, the formula for work would be f cos of theta, which is the force, and the displacement, which is in the direction of its line of action. And this is also can be converted into, we already know that f cos theta and dr can be represented as a dot product. So this is one of the application of dot product if you want to consider this in this way. So the work done is given by a dot product of two vectors. So basically it's the same thing if this was a vector f and this was a vector dr. So if you take a dot product of these two vectors, then also the result would be equal to the work done. Okay, so let's just define the unit of work, and then we'll go towards the principles of virtual work. So in SI unit, the unit of work is joule. And what is joule? A joule is a work produced by 1 Newton force that displaces through a distance of 1 meter in the direction of force. So if you apply a force of 1 Newton, and if you apply a force on 1 Newton and the object can displace itself for 1 meter, then this force is called 1 joule of work done. So because of this force, you will do a work of 1 joule. So that's how you define a unit of work. Now, what is a principle of virtual work? So for equilibrium, the algebraic sum of virtual work done by all the forces and couple moments acting on a body is 0 for any virtual displacement. So just like equilibrium equations, we also need to figure out if the virtual work done would be in equilibrium or not. So for equilibrium, the algebraic sum of all the virtual work for all the forces and all the couple moments is 0 for any virtual displacement of a body, then we can say that this system is in equilibrium. So what do I mean by that? And I will also explain in the next section when we will do example, and it will become clear how this virtual work works. So for now, for equilibrium, our virtual work should be equal to 0 for any virtual displacements. So let me give you an example. For example, you have a body which is on a surface. Now, this principle of virtual work says that we have to apply a virtual displacement. So we have applied this virtual displacement on a vertical, and then what we have to see is that we have to see the algebraic sum of virtual work done by all forces and couple moments. So here we have two forces. So this is the displacement. So this displacement is in the vertical line of direction. And which forces are acting vertically? You have weight which is acting vertically, and you have a normal force, a reactive force, which is acting vertically. So if we apply equilibrium, virtual work is equal to 0. So there are two forces which are acting in the direction. One is work and another one, one is weight and another one is the normal force. So you just also apply the delta y because this was the formula for work done. So what we will do now is that we will take delta y outside, so w minus n, and we know that it should be equal to 0 because of this condition. Now this delta cannot be equal to 0 because this is the virtual displacement which we applied. So the only option we have is w by n is equal to 0. So we know that weight is equal to the normal force. So that's how you calculate the equilibrium condition in this case for the virtual work. But this is important because the method of virtual work is particularly effective for solving equilibrium problems that involve a system of several connected rigid bodies. So this is useful. For example, in this case, this is an example where you have a system of connected rigid bodies, and in this case, the virtual work is much more effective than using the equilibrium equations which we were studying before. So the first step for this would be that we have to apply a displacement. So what we will do here, or angle. So what we will do here as a first step is we will apply a angle, a rotation. So let me say that I'm gonna apply this theta rotation and this delta theta. So if I apply this delta theta, this system of connected rigid bodies will have a new displacement. So this is the delta theta which I applied. So if I applied this, then the new location, the new orientation of this system of connected rigid bodies would be something like this. So by this we will figure out which of the force is responsible for doing this virtual work, and by using this and equation of virtual work we can solve this system of rigid bodies. So there is another figure shown here, and this is the delta theta, which is the virtual displacement we applied, and as a result of this we can observe two displacements. One is delta xb and one is delta yw. So first we have to find these two displacements. Now there are two reactions at point D, dx and dy, because it's a pin support, and also we have two reactions here, it's a roller support, so you will have one reaction by, and this is the force which is being applied as shown here. And also we have two weights. These two connected bodies will also have weight W. So the first step is to calculate these delta xb and delta yw, which are originated because of the virtual displacements which we have applied. So for delta xb and delta yw, first let's find xb. So what is xb? Xb is this distance, and which can be determined by finding this component of this body. So this is theta, so it would be xb, so this would be x, so this would be cos of theta 1, because this distance is 1 meter. So xb is, since these are 2, so you have 2 of 1 into cos of theta. Similarly, yb, you can calculate this this yw is this distance, and we can calculate it by using sine, because this is the theta and opposite of theta should be sine, and since it's half, here we can calculate 1 of sine theta. And if we take the derivative, then we will get this, and for w we will get 0.5 cos of theta delta theta. Now we have to apply the principle of virtual work, which is that the work done should be equal to 0. Now we have to figure out which are the forces which are acting in the direction of this rotation which we applied. So you have two weights, weight W, and weight W is acting in the direction of YW. And similarly we have two weights, so we will apply 2, and also we have this force, and this force is acting in the direction of xb. So force has delta xb. Now there are other forces also, for example this dy, dx and by, but these are acting in some other directions, not in the directions of xb or yw, so we will not consider this, and this should be equal to 0. Now what is weight? Weight is 9.81. What is delta yw? We have already calculated this one, 0.5 cos of theta delta theta. plus again same thing for another weight, and the force is 25, which is given, and this we have already calculated from here. Now we will just add everything, and if we add all the things then and multiply by 0.5, so we will get 98.1 cos of theta minus 50 sine of theta and delta theta, the rotation which we applied. So the rotation which we applied cannot be equal to 0, so all we are left with is 98.1 cos of theta minus 50 sine of theta is equal to 0, and the theta will go there, so it will become is equal to, and sine theta cos theta will go down, so sine theta cos theta is tan theta, so theta would be equal to tan inverse 98.1 divided by 50, which is equal to 63 degree. So the question was that we have to determine the angle theta, and by using the principle of virtual work we can calculate this theta as 63 degree. So that's how you can use principle of virtual work to solve the system of connected rigid bodies, which would be comparatively effectively you can measure these quantities as compared to the equilibrium equations which we studied before. So this is the last chapter for this subject, engineering mechanics. So see you in the other subject.